So Dr. Mostafa obtained his PhD in mechanical engineering from Babol University of Technology in Iran. Then he did, I think, several postdocs. The major one of them was in the university in United States. I don't remember, exactly, but he will show you. He has more than 70 journal articles with an H index more than 50. He's the author of 2 books for Elsevier. He's the author of several book chapters. He's the editor of the Journal of Scientific Report and several others. So here today he's going to present his work on, if I'm not wrong, supersonic fuel mixing. So I hope that we are all going to enjoy this presentation. Okay, Dr. Mostafa, can you share your screen, and start your seminar? Good luck.
Thank you. Hello, everybody. Good afternoon. I'm really happy to present my results and findings on fuel mixing in supersonic combustion chamber, challenge and future outlines. I'm happy to share my findings and results about fuel mixing in supersonic combustion chamber, challenge and future outline. First of all, I would like to introduce myself. I am Mostafa Barzegar, and graduate from PhD in mechanical engineering and now is a visiting researcher in C-MAST. I have graduated my master's degree in aerospace engineering. Then I follow my education in mechanical engineering, and I have been a visiting researcher in Stanford University for about 1 year. And now I am happy to join your lab as a visiting researcher. I am editorial member of a few outstanding journals like Scientific Report in Nature, and invited a special issue in 2 journals, as you can see here. I have also published more than 80 journal papers with issue index about 55 in high-ranked journals, and I have been a top 2% scientist for about 3 years, last 3 years, based on Stanford rankings. I also published 2 author book about supersonic, one about a scramjet engine, fuel mixing and injection system, and another about aerodynamic heating in supersonic and hypersonic flow, and also published 2 book chapters in different topics. Understanding a supersonic combustion. First of all, I want to present a schematic overview about the flow field inside the scramjet engines. Scramjet engines is divided to 4 main sections. At the first, the interflow is at the inlet, and the second stage is isolator. The third stage, which is known as a combustor, is the fuel injection occurs, and at the end, exhausted nozzle are released the propulsion power required for the hypersonic or supersonic flight. First of all, I want to explain a little about the complexity of the flow inside the combustion chamber. As you can see, there are lots of shock waves, which is very complicated without any fixed location in our we have seen in the combustion chamber. And the main challenge for such a problem is related to the speed of the flow inside the combustion chamber. As you know, we have several engines for vehicles for flight: turbojet, ramjet, and scramjet. The main difference of a scramjet from turbojet and ramjet is related to the speed of the incoming airflow inside the combustion chamber. As the velocity, the Mach of the free stream airflow is more than one, which is known as a supersonic flow inside the combustion chamber. This engine is related to a scramjet engine, which no reduction of the incoming airflow inside the combustor, and fuel injection should happen at a short time and with high efficiency. It's very crucial for the overall performance of the supersonic and hypersonic flow, although it has a little time for injection, mixing, and combustion stability. As you can see, there are lots of injection system which is appropriate for the combustion chamber inside the scramjet engine: a step injection, cavity injection, porthole injection, film injection, and other types. The important things associated with these combustion chamber, this injection system is related to the desire of the engines. The most conventional type is related to transverse injection or porthole injection. As you can see in the right side, you have lots of different shock wave happens near the injection system when the supersonic flow coming and encounter the cross jet upstream circulation zone, separation shock wave, Mach-Dis, and all of these shocks happens at a very small region near the injector. Careful attention to these points is very crucial because it's a key point for the efficient fuel mixing in our combustor. Look at the downside. If you look here, you can see that the counter-rotating vortex pair is generated by the injection of the cross jet when encounter a free stream. This counter-rotating vortex pair is along with the horseshoe vortex region happens downside of the counter-rotating vortex and the wake region, which is very important. At the left side, schematically demonstrate what the complexity of the flow when the use of shock generator along with cavity flame holder. It results in the usage of any shock generator inside the combustion chamber results in bow shock, separation shock wave, shear layers, main circulation, which is very crucial in combustion chamber. First of all, I want to introduce our methodology for the simulation of these innovation. For simulation of the cross flow jet inside the combustor chamber. As you can see in the left side, you have seen that flow field domain is very large, but we have selected a specific region upstream and downstream of the injector for evaluation of the fuel mixing in this region. As you can see, we have developed a new injector types, which is lobe injector nozzles for fuel mixing inside the combustion chamber. We have examined a 3-type 2-lobe nozzle, 3-lobe nozzle, and 4-lobe nozzles with inner air jet for combustion chamber. As you can see, although the selected domain is not very large and spaces, but the grid generation for our model is really high because there are lots of critical regions near the jet injection region where jet encounter a free stream and result in different regions and problems. First of all, I want to introduce a few effective parameters which will be evaluated in our studies. The first one is about the fuel penetration height, where the hydrogen mole fraction of the jet balloon reduced to 0.05%, which is known as a fuel penetration height. The second factor is very important. We have known as a circulation factor. Evaluating the vortex structure of the flow in our model. The third one, which is very important, and all the evaluation of the any injection system is based on this factor, is known as a fuel mixing efficiency. The formula for the calculation of these three parameters are presented in my slides, which is very important, and we'll discuss in the next chapter about how these factors change along our study. First of all, as you know, the first important step for the evaluation of the results, computational result, is a validation. We have evaluated our data based on the penetration height, which is the normal data available for all the case. First of all, we examine just a single circular jet, and our data are achieved data, which specifically penetration height is evaluated downstream of the jet and compared with other experimental and computational data. And our achievement agrees well with others' data as presented in my slide. And in the right side, we have also known that we should examine our data, our generated grid for evaluation of grid independency analysis. As you can see, we have examined three different grids, and we have seen that the normalized velocity profile is agrees well with computational data, and it confirms that a generated grid, a fine grid, is acceptable for our investigation. In this slide, I explain about the main feature of the cross-jet flow, encounter the free stream and fuel mixing zone downside of this. As you can see, the difference of the injector greatly influence on the shock wave interaction in our model. You can see that if change the injector from 2-lobe injector to 3-lobe injector, the upstream circulation is strengthened. These regions and fuel concentration downstream of the jet is completely different in these three injectors, although it seems that this injector is not totally different, just a little different in our injectors outlet. As you can see in the right side, flow jet interactions in these three models is really different. This is this is related to the nozzles type and usage of inner air jet, which is very important. As explained in previous slides, you've seen that the air jet flow is released from the internal nozzle for efficient fuel mixing. And our achieved data confirm that these injection totally increase the interaction of the flow. In this slide, I'll demonstrate the mixing zone, and especially, as you can see here, produced upstream vortex, which is the region where our horseshoe vortex initiated. In the left side, I demonstrate how these vortex trail to downstream. The main vortex, as you can see here, this is known as vortex pair, as I show in the schematic flow field. And the second one is related to the horseshoe vortex, which is different for these different geometries. And when it moves downstream, the strength of the horseshoe vortex is weakened, and the main flow is related to vortex pair. As explained in the initial slides, there are lots of important factors for the evaluations of the flow and mixing inside the combustor. Evaluating of the circulation is very important. As you can see here, the 2 and 4 lobe injector has the same vortex or circulation factor along the downstream, while however the 3 lobe injector results in a different strengths of the vortex circulation strength downstream the injector. In the right side, the effects of these injectors on the fuel mixings are presented. As you can see, the 3 lobe injector has a higher fuel mixing, especially far from the injectors. In order to improve the performance of the fuel mixing inside the combustion chamber, we have used a shock generator, which is demonstrated here as a wedge in upstream of the flow on top side, which is result in the creation of the bow shock, which results in the efficient fuel mixing downstream. In the right side, you can see how the flow changed, especially when shockwave generator is used. The clear distinct difference between previous the usage of the shock generator is the strength of the upstream circulation, which is result in which intense and improve the fuel mixings near the jet. Comparison of the fuel mixing of these 3 injectors are also confirmed that fuel mixing is improved by using a 3 lobe nozzles, 3 lobe nozzles with a shock generator has a higher fuel mixing inside the combustion chamber. The main change we have done here is to replace a single 3 lobe, 2 lobe, 3 lobe, and 4 lobe nozzle with multi equivalent nozzles with the same type. Changing a single circular with a multi-jet significantly improve our fuel mixings in combustion chamber. As you can see, the flow field and the growth of the penetration height is the main change associated with the change of the replacement of the single jet with a multi-jet. Here we used we change a single jet with 4 multi-jets, and you can see here the flow here completely change due to interaction of these jets with each other and creation of the extra circulation and vortex in our model. In the right side, the evaluation of the flow on 2 plane downstream of the injector clearly shows that the usage of a multi-jet significantly improve the fuel mixings and especially the vortex pair and circulation downstream of the injectors. In the next step, we have developed our multi-jet with a 2 lobe, 3 lobe, and 4 lobe injector with a new idea. The idea of improving the increasing the height of the nozzles each other. As you can see here, the second, third, and the fourth injector is extruded from the bottom, and these techniques clearly increase the interaction of the free stream with the injectors. As a display in the previous slide, you can see that the interaction of the last injectors with the free stream is under the shield of the upstream injector. But when we used an extruded configuration or arrangement of the injector, the interactions of the fuel jet with the free stream is preserved and maintained along downstream in the proposed models. You can see how horseshoe vortex trail downstream in the up figure. In the down figure, you can see how the oblique shock. Here, we used the shock generator for the development of the single extruded injector and demonstrate how use of the shock generator results in oblique shock and separation shock in our model. Today, we have listened much about machine learnings. Recently, the application of using machine learning is significantly developed for computational studies. The main outline of this technique for the fuel mixing is to optimize of the fuel efficiency. Then we want to predict the fuel jets and reduce the cost of the computational time. As you know, the main challenge of the real modeling of the fuel injection is related to the analysis of a real feature of the flow in a transient injection. As you know, the injection process happens at a very short time inside the combustion chamber, and this intensify the importance of the real data, the prediction of the flow for the whole time, whole injection time. So machine learnings help us to improve our data for the prediction of the fuel mixing. Just for example, if the simulation happens, if the injections in the transient phase happens in 1 minute, you can just use just half of the time step and then use the machine learning for the prediction. In addition, as you can see in the right side, the size of the DNS simulation of the combustion chamber has significantly increased in recent years. And also the number of generated grid points for the simulation of the combustion chamber have increased. The use of the machine learning significantly improved the accuracy of data, reduced the time of the simulation, and analysis of the data for the different time steps inside our combustion chamber. The most conventional type of the machine learning technique for the prediction of the flow is known as convolutional neural network, or which is known as a CNN. In these techniques, they analyze, they achieve data. For example, a snapshot of the flow, which contains a velocity or mass or temperature of the domain, and use this approach approach for extractions of the main data associated with the flow, and use these techniques for the prediction of the other time steps. As you can see, the first step in the CNN classification and feature extraction used, for example, data, achieve data, and then used several convolutional technique for achieving a row of data, which is used then achieved data is then classified by MLP techniques to achieve 2 or 3 significant data associated with these data. This technique is also validated with decoder. Use the encoder for compressing the data and using the decoder for expanding the data and evaluate. And these techniques completely preserve our data in encoder and decoder. The second popular technique for our models, which is used in our investigation, is the proper orthogonal decomposition, and it's combined with LSTM. In these techniques, we have used a few initial time steps for prediction of the flow. This schematic figure demonstrates how these techniques operate in our models. You have extract initial data, important data, for example, main flow parameters, and then use a train and test split our data to train and test and evaluate our precisions by these techniques. Here is the result of our first simulation with a POD LSTM technique for the prediction of the fuel inside the combustion chamber. As you can see, if our time step trained for about 60% in the upper side, you can see that the prediction for just one stage is good. But if we want to predict with higher precision, we should have a more available data, which is which demonstrates a higher accuracy for our results. When we have trained our data for 0.9, we can see that the prediction are more accurate in for our models. The future outline of fuel injection system. Today we have several researchers have tried to enhance computational fluid dynamic modeling. One of our techniques, which is very used here, is to use different techniques and combine these techniques with the machine learning to achieve reliable results and develop a new idea for efficient fuel mixing. The second concept, important concept for the future models for injection system is using a nanoscale fuel injection, which has a lot of application in recent devices. The third important outlines for fuel injection is using the active control system. Active control system dynamically adjust the fuel injection parameters based on the real-time performance data, optimizing mixing and combustion. And the fourth, but not the last concept for the future injection system is multi-model combustion system. Most of the present injection system is specified for a limited range, but in the future we have seen that adjusting the combustor based on the flight speed is the main attribute of researcher in this topic. I have also used a CFD for other applications and other problems here. Besides the fuel mixing, I have motivated to use the CFD method for biomechanics, which is my favorite topics, which is I follow after my graduation, which is an analysis of the flow, blood flow inside the cerebral aneurysms, and I used these techniques for the evaluation of the blood hemodynamic inside the cerebral aneurysms and estimation of the hemodynamic and risk of aneurysm ruptures via CFD is very important because it's really related to human life. The importance of the human life and healthy is clear for everybody, especially after COVID-19, which is a very critical issue for everyone, especially as you know, the formation of the aneurysms, especially saccular aneurysms, results in the important challenge for everyone's and the rupture of this results in the bleeding. We have used the non-Newtonian models for simulation of the blood inside the different cerebral aneurysm and evaluate how the usage of the stents and the deformation of the aneurysm could reduce the risk of aneurysm ruptures. Thank you everybody for listening me. Thank you everybody to participate in my presentation. I'm really happy to share my achieved data and my findings in different topics, and I'm ready to answer any question from you.
Thank you so much, Dr. Mostafa Barzegar. So, thank for presenting us your work, and your recent work for us. Hope that we can, have your presence in our research center more, and we can use your knowledge for our future collaboration. Thank you so much.
Thank you very much.
You are welcome.